Hello, everyone. In this section, we're trying to discuss machine learning landscape and build a machine learning project. Specifically, we want to discuss what is machine learning. So what is machine learning? Machine learning is the science and art of programming computers so they can learn from data. That's one way to look at it. And also Arthur Samuel in 1959, he defined machine learning this way. Machine learning is a field of study that gives computers ability to learn without being explicitly programmed. So meaning learning from the data. Tom Mitchell, 1997, who is actually a professor at Carnegie Mellon on machine learning, he defined machine learning in the following way. A computer program is said to learn from experience E with respect to some task T and some performance measure P. If its performance on T, as measured by P, improves with experience E. Again, learning from data and improve the performance. So some examples of machine learning algorithms, for example, one of them spam filters. So you're probably aware in Gmail, for example, there is a specific function, um, spam filtering. And then how exactly Gmail figured out some of the emails can be put into spam. It's just based on learning, based on data, and come back with some sort of labeling. Another example would be recommendation system, like in Amazon recommendation systems and Netflix recommendation systems. So essentially, it gives you some recommendation based on what you viewed in the past, and also based on what you purchased in the past. And one more example is customer segmentation. So in marketing department, a key decision that they want to make is how can we differentiate different marketing strategies for different customers? So in order to understand the customers, you have to do customer segmentation so that you can come up with different marketing strategies for different types of customers, such as you could marketing through direct mail, or you could marketing through a phone call, or you could marketing through some sort of promotion by mail or email. So these customer segmentation would help the marketing department to make a decision. Why do we use machine learning? So let's look at this, that we're not using machine learning yet. So what you do is you start with the problem and you study the problem, you write some rules, and you evaluate. If you think the evaluation comes out to be great, then launch the program. Or you evaluate, you find it's not really doing a good job, and then you go back trying to study the problem again to try to write rules one more time. And then turns out to be you have to write complex rules for your system, which is less than ideal. Now let's look at how we can embed machine learning in this process. So instead of writing complex rules in this section, you could train your machine learning algorithm based on data to learn the rules. So in the spam filter example, machine learning techniques automatically learns which words and phrases are good predictors of spam and then label them as spam. So that's a perfect use case for machine learning. And even better, a spam filter based on machine learning techniques automatically notices that for you has become unusually frequent in spam flagged by users, and it starts flagging them without your intervention. So based on the data, you want to update the data and train your machine learning algorithm, evaluate your solution, and launch the spam filtering methodology. And then with more and more data coming in, you want to update your data and train your machine learning algorithm. So it becomes a automated cycle and process. Even better, machine learning can help human learn. They start with study the problem, train your machine learning algorithm with lots of data to train your machine learning algorithm, come back with some sort of solution, and then we inspect your solution, try to understand the solution, and to check whether you have some sort of insights from the solution. If indeed you get more insights of the solution or the problem, you understand the problem better and iterate if needed, study the problem, so on and so forth. So applying machine learning techniques to dig into large amount of data can help discover patterns that were not immediately apparent. This is another reason that we're learning machine learning. So let's look at, as a summary, problems for which existing solutions require a lot of hand tuning or long lists of rules. One machine learning algorithm can often simplify code and then perform better. So instead of writing complex rules, you could leverage machine learning algorithm. Complex problems for which there is no good solution at all using a traditional approach, then the best machine learning algorithm can actually find a solution. So in the first case, it's just complex without machine learning. Machine learning helps you to simplify the process. In the second case, traditional methodology cannot even find a good solution, but machine learning can help you. Third possibility and the reason is fluctuating environments. A machine learning system can adapt to new data. This is the key of machine learning. It can learn from new data and get new insights from the new data. And one more reason, getting insights about complex problems and large amounts of data. These are the key reasons that we want to use machine learning. Let's take a look at some major types of machine learning systems. Here is one way to differentiate different machine learning systems. It's called supervised learning, or unsupervised learning, or semi-supervised learning, or reinforcement learning. So let's take a look at exactly what all these are. First of all, you could differentiate by saying that whether or not the systems are trained with human supervision. If there is human supervision, then it's majority of the time would be supervised learning or semi-supervised learning. Without human supervision, then majority of the time would be unsupervised learning. And another way to look at it is to see whether or not the data has labels. If the data has labels, then it's supervised learning. If the data has no labels, then it's unsupervised learning. So let's look at this example. You have a bunch of training set. And then for a different instance or email, you have a label to see whether it's a spam or not. It's okay, it's not a spam. This one is a spam. And then you just learn from this training set to understand which are the ones are going to be spams. Once you learn this, you kind of know the rules, learning from the data, the rules learning from the data, the rules learned from the data. Once you have those, you could apply the rules on new instances and try to make a prediction whether the new instance or new email is a spam or not. So this case is a supervised learning because the data is already labeled as spam or not. If it's not labeled, then we know it's going to be unsupervised learning. We're going to discuss all of this a little bit as well to give you more clarity. For supervised learning algorithms, these are the key types of algorithms, including k-nearest neighbors, linear regression, logistic regression, support vector machines, decision trees and random forests, and neural networks. I know some of these are probably a little bit unfamiliar to you, or maybe you're only familiar with one or two. Good news is we're going to learn all of this for the whole semester. For unsupervised learning algorithms, data has no labels. For example, this is unlabeled training set for unsupervised learning with the hope that you would be able to differentiate this group versus different groups if possible at all, and doesn't have any label. And then in terms of unsupervised learning algorithms, you could use clustering algorithms, k-means, dbScan, HCA, or you could have anomaly detection and novelty detection type of algorithms, SVM, isolation forest, and you could have visualization and dimensionality reduction, PCA, kernel PCA, LLE, TSNE, and also association rule learning, a priori, and ECLAT. So these are the type of algorithms for unsupervised learning, and we are going to study some of these as well. So this is the output. For clustering, we are hoping that original data has no labels. Based on feature 1 and feature 2 in the data specifically would be columns of the data to understand just different dimensions of the instances or the raw data. And then with the hope that by analyzing those dimensions, you're able to differentiate each observation from the rest of them. Or some similar ones, you can group them together. So in this case, we are able to differentiate this group with this group, and even with that group and this group. So this methodology is called clustering that we're going to discuss later in the semester, and you should have a lot of exposure to this. Semi-supervised learning. So some data has labels, some does not have. Then for example, some of them are labeled as triangle and some of them are labeled as rectangle, and a bunch of them don't have any label. The question is, for this particular one, which class it should belong to? Is it green triangle or yellow rectangle? So this type of algorithm is called semi-supervised learning. Let's look at reinforced learning. Agents select and perform actions and get rewards in return, or penalties in the form of negative rewards. For example, this agent, right? And then he look at the environment and he want to observe the environment and select action using the policy. So what he made a decision is, let's go to try to get close to the fire, and he got penalized. Ouch. He got deducted by 50 points, and he basically get a penalty, right? Now he realized, oh, the fire is bad. It's something really hot. Next time I should try to avoid it. So then what it does is, okay, let's update that policy, trying to learning in the learning step, try to update that policy, iterate until an optimal policy is found. Maybe next time he realized, oh, that's fire, I should put some water to try to put it off. So this type of algorithm is called reinforcement learning. And one more different differentiation direction is something called batch learning versus online learning. So what it does is used whether or not the system can learn incrementally from a stream of incoming data. If it's trying to learn by batch, then it's called batch learning. And the online learning itself is really just real-time learning. And a lot of algorithms require this online learning. And one more differentiation of machine learning algorithms based on is going to be based on this perspective. It's instance-based versus model-based learning. It's essentially trying to differentiate by how they generalize. For example, instance-based learning, this is called instance-based learning when the system learns the example by heart, then generalizes to new instances by comparing them to learned examples or a subset of them using a similarity measure. That would be instance-based learning. The other way is to generalize from set of examples is to build a model of these examples, then use that model to make predictions. So in that case, we call it model-based learning. Rather than just purely based on memory and the similarity, it's really build a model to generalize that. So that's the differentiation between instance-based versus model-based learning. So here, this graph want to illustrate the importance of data versus algorithms. So point here is, once you have a bunch of more data, your algorithms tend to kind of converge. Unfortunately, majority of the time, we actually live in this insufficient quantity of training data uh, um, world, meaning that the access, we don't have the luxury of 1,000 millions of data points. Majority of the time, we probably live in a world of less than 1 million or maybe a 0.5 million world. And then in that case, your algorithm tend to differentiate in terms of accuracy. That's exactly the reason that we're learning the best algorithm among the small set of data that we are able to observe. So main challenge for machine learning is really insufficient quantity of training data. Another challenge is non-representative training data. So in this example, assume that we're looking at GDP per capita versus life satisfaction. Assuming that we don't have observations for these red dots, we're just missing some observations. In that case, what happens is you're going to model this as a linear regression and turns out to be this dotted line, versus if you do have these observations for the red square, then you probably end up with this solid line. You can see that it's kind of different, right? So the slope is different, the intercept is different. That's why we hope that we have the full picture of the training data, meaning that your sample that you're collected for the problem that you're trying to solve have representative or have representation of the population if possible at all. Here are other potential challenges. We just discussed insufficient quantity of training data and non-representative of training data. Or some other potential challenges would be poor quality of data. Errors, outliers, and noise are in the data. You have to deal with them. Irrelevant features. Some of the columns or features are not as useful as you thought. And then you end up with the suffering of garbage in and garbage out just because your features are not so useful. Turns out to be the case that your model are not so useful. Some other two challenges would be overfitting the training data or underfitting the training data, which we are going to discuss next. So what is overfitting the training data? So essentially that we're trying so hard to build a model to connect all of these kinds of points, and then it turns out that we're not able to generalize this model at all, meaning that this data fits the training data very well, but it's not going to do well for some unseen data. This type of problem is called overfitting. So what you can do is you would try to regularize your model so that that can reduce the risk of overfitting. You could also adjust hyperparameters. So for example, if you have all the data, you have this red line being your prediction. And then if you don't have all the data, you have this dotted line, blue line, to be your partial linear model on partial data. Good news, if you regularize your model with partial data by regularization, which we're going to discuss later in the semester, and then you would show that the solid blue line is a regularized linear model on partial data, which is actually doing a decent job on the data. And then it reduces the risk of overfitting. Let's look at underfitting. Underfitting the training data, it occurs when your model is too simple to learn the underlying structure of the data. In that case, what you want to do is you select a more powerful model with more parameters, or you feed in better features to the learning algorithm. So this is a process that we call feature engineering. We're going to discuss PCA, principal component analysis, to reduce the dimension of the features which belongs to this field. And you could also reduce the constraint on the model. Example, reducing the regularization parameter. So these are potential ways to solve the problem of the underfitting the training data. Underfitting meaning that your model is not able to do a decent job on your data. So what you can do when you try to build machine learning model, what you need to do is you at least have to have a training set versus a test set. And usually you could leverage 50 to 50, or maybe even 80 to 20, or 70 to 30. It's really depending on the problem, depending on your personal choice. I would suggest that you could do 80 versus 20 or 70 versus 30. And then you get some out of sample error called generalization error on the unseen data so that you are able to evaluate your model. You need to do hyperparameter tuning and model selection in your whole model building process. Last thing that we want to touch upon is something called no free lunch theorem. So in a famous 1996 paper, David demonstrated that if you make absolutely no assumption about the data, then there is no reason to prefer one model over the other. This is called the no free lunch theorem. For some data sets, the best model is a linear model, while for other data sets, it is a neural network. There is no model that is a priori guaranteed to work better. hence the name of stereo. So meaning that you just don't know which model is going to work well on what type of problem. No free lunch. So you have to go through the data and work on some algorithms and try to help you to make a decision on which might work better to your data set. This actually concludes our discussion of what is machine learning. What I want you to be aware is you need to know what is the difference between supervised versus unsupervised learning, and what is the idea of regularization, and what is underfitting, what is overfitting, and this idea of testing and validating as well. This really serves as an introduction to machine learning, and as the semester progresses, you would learn more of all of these algorithms. Thank you.